Hello, this recording covers the questions asked in office hours on Friday regarding Unit 3, Module 2, polymers, and the first part of charges in Unit 3, Module 3. Okay, so polymers here. So our general model is that we have a double bond and a side chain, right? So the double bond is here. Here, and there's our what we call the side chain. And so what's going to happen is this double bond is going to, one of the bonds is going to break open to create new connections, and the side chain does not change at all. It remains the same. Right, so what we're going to do is take the double bond. We're going to have the single bond there, but now what we do is we put the two electrons from the single bond, and what's going to happen is each one is going to go, the one on the right is going to go to the right, make a new bond. The one on the left is going to make a new bond, and we sort of put a bracket like that. So that's our model. The double bond is split, and we did this in class by opening our hands. Our hands are each electron to make a new connection. All right, so when we do that, what we see, it would look something like this. This was the original bond, right? The original bond was here. That was the double bond. But then it goes away, right? Goes away. And it creates the new single bonds, right? So that dash is where the double bond used to be. And now it's created two new single bonds, right? One on the right, or one on the left, and one on the right. So because that double bond broke, it now links to the left and to the right. Okay, we see that's answer C. If we look at the other answers, A is wrong because now the side chain is wrong. It has a hydrogen there, wasn't there in the original polymer. B is wrong because the double bond hasn't been broken. The double bond needs to break so that it can make the connectors. And then D is wrong because it has the wrong side chain. So in our polymer model, you just want to make sure that you don't change the side chain, number one. And number two, you need to open up the double bond, leaving behind a single bond, and then you create a bond to the left and a bond to the right, which you then put the parentheses around, right? So you put the parentheses around on those new bonds made. Okay, so this, now the question, we often ask questions not about which monomer makes a polymer, but for example, how can we make something more rigid or absorbed more in water? And so we're going to take a look at this one. Okay, so in this case, we want to know which of these substitutions on X would not make this polymer more rigid. All right, so let's take a look at the first one. So the first one says add CH3, CH2. Well, that's adding a branch, right? It's a branch that it's going to prevent contact, and if it prevents contact, then that's not going to be more rigid. It's going to be less rigid. So this is a good answer. It's less rigid because you've introduced branching. Now, adding iodine means you've now added more electrons, which are going to make it more rigid without adding branching. Right? You didn't lose any contact by adding this atom. Same thing with 3. You've now added more dipole-dipole interactions and hydrogen bonding interactions without any loss of contact, right? So that's the key. You can add, so there's no contact, there's no branching, there's no additional atom. I mean, there's one atom that's added. In X, you're adding a group, right? So, but you're not adding multiple atom connected like the carbons. So for this case, we would pick 2 and 3. Oh, No, 2 and 3 would make this more rigid. So this would be 2 and 3 would be a recipe to make it more rigid. But if our goal was to make this less rigid, right? Less rigid would not make. Then the answer would be Roman numeral 1 because of the additional branching. 2 and 3 would make it more rigid. All right, so that's at the side chain level. Let's take a look at the polymer chain level. So the polymer chain, like how many of these polymers should we have? And so when you look at this is our dispersion forces, go with total number of electrons, number of atoms, right? As that goes up, so do attractions. So the longer the chains are, the more rigid, the harder we expect those chains to be. Okay, so there's two ways to make these chains stronger. You can make them longer, right, so they interact more, or you can add more electrons without branching. Okay, so this question was asked a couple students. So we want to determine the charge on X here, given that it forms this ionic compound with sulfur. All right, so Unit 3, Module 3. Okay, so what we're going to do is look at, well, what is sulfur's charge? So we see sulfur is in the second column over by the noble gases, so it's a negative charge, and it's right below oxygen, so it's a -2. All right, so there's an equation. So what we could do is we're just going to add up the charges. We don't know what X charge is, but we know that 2 sulfurs at -2 is -4. And when we sum all these charges up, it has to be the total charge of the ionic substance. Now the total charge of the ionic substance here is 0. So we can solve for X. Solve for X, and if we do that, X equals +4. So if X is +4, then it would require 2 sulfurs at -2 to add to it to obtain 0. Select the correct chemical formula for the ionic compound of barium and fluorine. So let's take a look. First of all, where is barium? Okay, so barium is, you kind of go down, it's like row 4, 5, 6, right next to cesium, but it's in the column, second column, so it's +2. Right above, and you could find it, right below calcium and potassium. Then we look over at fluorine, and fluorine's -1. So we put these charges together. Barium 2+, fluoride -1. Then what we do is we do the swap the charges and put them as subscripts. And if we do that, we get Ba1F2, or just barium fluoride, BaF2, and we double check the charges. So if barium is +2, 2 fluorides at -1, we sum those together, it equals 0, and our total charge is 0. Okay, and here we have our final polymer question, which is we want to make what modification would make water stick less to this material? Okay, so would replacing the CH3 groups with OH groups, well, that wouldn't do it because that would interact too much, right? It would make it too much by this would introduce a more hydrogen bonding and dipole-dipole interactions. Replace CH3 with H atoms. That's a good one. right? So in that case, we would have only CHs present. Replace the CH3 groups with CH3, CH2. So this would also be a good answer because you could, again, water would stick less to these groups if they were completely nonpolar. And the last one, replace it with CH3. No, we wouldn't want to do that because this group can hydrogen bond and is also polar. So two possible answers here. We could put H atoms there, or we could put carbon hydrogen there. If we were to say this is probably the best choice because by adding more carbons, atoms there, we would expect there to be less interaction with water, nonpolar interactions. Okay. All right, and so for our final problem, we are given that the submicroscopic representation, looking for strontium carbonate. Okay, so what we're going to do is first, we're going to recognize that this is molecular 2-to-1. This is molecular 1-to-1. And so these can't be choices because they're not ionics. So ionic substances, this is a metal, and these 8 that also tells you, so ionic, so it has to be a solid, right? So all ionic substances are solids. So the question is it 1-to-2 ionic, or is it 1-to-1 ionic? Okay, so when we look at the periodic table, what we see is strontium is here. So at +2, so strontium is +2. We look up carbonate. So carbonate is has a charge. Mostly we just need its charge. The charge of carbonate is 2-. We'll talk about these substances in more detail. When we look it up, it's 2-. So we have this carbonate, same charges. So 2 and a 2 here, which means it's strontium CO3. So it's 1-to-1. So this is a 1-to-1 metal, and we would pick this substance. So when we look at the submicroscopic representation, you want to make sure that you identify the charges, and then once you have the charges, you can then use the swap method to determine the subscripts. And if the subscripts are identical, then you know it's 1-to-1. Okay, these are all the questions that were asked during office hours on Friday.